Hi everyone, so today we're going to continue on our discussion on oscillation in 11.4. So last video we get to talk about what's the differential equation that will model an oscillation and also make our first assumption, which would be no friction, no resistance, and also no external force. And we realize that in that case we have what we call a harmonic or free oscillation, where the piston would likely continue to move forward and back forever because the displacement result in a cosine curve which will go on forever. Now, of course, that's, as I said in the last video, that represents what we call the ideal scenario, where there's no external force and there's no resistance. But more realistically is that there will be some kind of resistance unless you are really in a true vacuum. Otherwise, there will be some kind of resistance, however small it is. Even air would have resistance. So therefore, let's talk about a second scenario, which we're going to call that the damped oscillation. So in this case, we're going to assume that if K is not 0, then the fluid, and yes, air is considered to be fluid, is exerting some kind of resistant force on the piston, which is a damping force that slows it down. So without any external force being applied to the pistons, this friction would eventually slow the piston down until it stops. Unless there's some kind of external force that compensates this resistance. Otherwise, if there's no external forces being applied, to the piston, the friction will eventually, however long it takes, but will eventually slow down the pistons until it stops. And in this case is called a damped oscillation. And in this case will be described by the differential equation. Because of no external force, it is still a homogeneous equation. Mx double prime plus kx prime plus hx equal to 0. Now, once again, what I'm going to do is the following. Actually, maybe I'll do this. Once again, I'm going to do the following, because m is a constant which describes the mass, which cannot be 0 or negative. What I'm going to do is divide the entire equation by m, and that gives us this equation. So this is the equation we want to study. Now, important to realize is the following. This equation has a characteristic equation. R squared plus k over m r plus h over m equal to 0. Now this is a quadratic equation, and this quadratic equation has 3 distinct types of roots. And because of these three types, it would generate something very different. But how do I know what type of roots they are? Well, the type of roots is actually dependent on the discriminants. And once again, you're probably thinking, like, when you're back in Algebra 2, why do you have to learn discriminant? Why don't we just find the root instead of trying to describe what the root is? Well, because in some cases we don't have enough information to solve for the roots, but we simply want to know what kind of characteristic, what kind of things would happen based on what the root is. So the type of the characteristic roots is determined by the discriminants. And by what you remember, probably learning core nature of the roots. So the discriminant is basically b squared minus 4ac. In our case, b is k over m, so become k over m squared minus 4 times a is 1, c is h over m. And so what is the discriminant turn into? I'm going to just call the discriminant d, which is k squared over m squared minus 4h over m. So that would be what our discriminant is. If I want to take a step further, I can say, well, let's combine them with the same denominator, and the numerator become k squared minus 4mh. Notice that the m squared on the bottom is always positive. So therefore, technically the value of the discriminant is actually determined by k squared minus 4mh. So that is what we're going to be using to examine what's going to happen. So as I say, there are three distinct types of roots. So let's talk about each of them. So let's start with case 1. Case 1 is the following. What if k squared minus 4mh is greater than 0? Okay. That would imply that our discriminant is greater than 0. Okay? And that would mean that our k is actually greater than 4, or actually 2 square root of mh. So that is how we go identify what happened. If the constant for the resistance is greater than the value, the numerical value of 2 times the square root of mass and the Hooke's law constant, then in this case, the characteristic roots are both real and distinct. So we don't have a repeat roots, but we have 2 real roots. Because of the fact that h and k are both constant, and as well as m are constant, since k over m and h over m are both positive, the 2 roots must both be negative. And if you think about it, it makes sense, because if you think about factoring, if you have both the b and the c are positive, then when you factor, you have to have 2 factors that have like x plus r and x plus r1 and x plus r2, therefore result in both r1 and r2 being negative. So therefore, in this case, we can say that the 2 roots let's say the two roots are R1 and R2 are the characteristic roots. And let's say R1 and R2 are both less than 0. So therefore they're both negative. Then what will the solution look like in this case? The solution x of t will have to be in this form. C1 e to R1x, or C1 e to R1t, plus C2 e to R2t. Now, because of both R1 and R2 are negative, this x of t would basically decreases exponentially. Well, actually, it may not necessarily be exponential, but decreases as t increases. As a matter of fact, if you think about it, as t go to infinity, x of t will approaches 0, as both of t's become 0 plus 0. Okay? In this case, this is called over damping, which describes the scenario where the object would fail to oscillate. In this case, is over damping. The friction is too great for the pistons to oscillate. So it just slowly return to the equilibrium position, which is represented by x equal to 0. If you think about graphically what happened in this case, it basically has the following things, really depending on the initial condition. So therefore I cannot really draw you one graph, but most likely will be something like this. It will probably start off and go up and then maybe just level off. Or in some cases, oh, that's x. Or in some cases, it will go off and then cross over the equilibrium side and then eventually level off on the other side. What it would not do is, or very unlikely to do, is that it will cross over a second time. It will probably just cross over at most one time, and then it would eventually just level off into the 0, which is the horizontal asymptote. Okay? And of course, it doesn't have to be like go up and down. It could actually be something like this. It could go like this. It could also go like this. Okay, so it really depends on the initial condition as well as the initial velocity, whether it would go away from the equilibrium or go toward the equilibrium. But the key is that they will at most crossing the equilibrium at maybe one point at most. Okay, but it would not oscillate back and forth. Case 2. What if k squared minus 4mh is less than 0? Therefore, indicate that the discriminant is less than 0. Or k is less than 2 square root of mh. In this case, the characteristic roots are imaginary, are actually complex conjugates. And the general solution will be in the form of, so our typical complex solution, complex characteristic root general solution, which would be x of t equal to c1 e to the at cosine bt plus c2 e to the at sine bt. So if you think about it, notice that this actually works out almost identical to what we already talked about right here in the free oscillation, where if you look, our solution almost have the same exact form, c1 cosine something t plus c2 sine something t, except the only difference now is that we have a e to at in front. And because of that, we can actually go for the same argument, which I'm not going to do, to rewrite this into this form. Which is basically the same form as the free oscillation, except we have the e to at here. Okay? And in this form, we can define A to be equal to, same thing, square root of c1 squared plus c2 squared. And theta, which is the phase angle, would basically be the tangent inverse of c, c2 over c1. And our alpha, or our A would actually equal to negative k over 2m. And our B would actually equal to the square root of the discriminant, but because the discriminant negative, I have to pull out the I, and therefore it makes the discriminant flip backward. If you put k squared minus 4mx, you get a negative number, so that doesn't work, over 2m. If you wonder where A and B come from, it comes straight from the quadratic formula, actually. If you go through the quadratic formula, you'll see that. And this basically gives us the scenario right here. In this scenario, what happened is, in this case, the friction is small so that the piston can actually oscillate until it eventually stops. And this is called underdamping. In this case, the reason why it has to be underdamping, and it would eventually stop because, once again, the A value is negative, and therefore making the fact that when t approaches 0, e to at would approach, when t approaches infinity, e to at would approach 0, therefore forcing the entire x to go to 0. So here, make sure you understand that as t go to infinity, e to the at will approach 0, and therefore x of t will also approach 0. So how is that different than overdamping? Is in the fact that this case, what happened would be the following. Oops, x, I'm sorry. X is that it will start off and then we'll go across and then we'll go back up and then down and then up and then down and then up and down, up and down, up and down, until the oscillation becomes so small that we can kind of say that it's kind of stopped. And that's what underdamping is. The last case. what happened if case 3? What happened if k squared minus 4mh actually equal to 0? Or basically, what happened if the discriminant is equal to 0? Or basically meaning k is actually equal to 2 square root mh. In this case, the characteristic roots are real and equal. And in this case, the two characteristic roots R1 and R2 both equal to negative k over 2m. What would happen to the solution? The general solution in this case is x of t equal to c1 e to the negative k over 2mt plus c2t e to negative k over 2mt. What happened in this case is that it actually lied between the overdamping and the underdamping. This case kind of lied between overdamping and underdamping. The way that it is right now, because it's in the absence of the cosine and the sine, it will not oscillate. Okay, so this one does not oscillate at all. And in this case, this is called critical damping. Because any small changes in the value of k, m, and h will disturb the equality k equal to 2 radical mh, which will result in either under or over damping. The way that it stands right now, it will behave more or less like overdamping, because it would not oscillate without the sine and cosine. So therefore, it would more likely have the same graph as what you remember seeing in this case, where it might cross over once, or it might not cross over at all, but it would just slowly get to the equilibrium without actually bouncing back and forth. Okay. I guess we'll talk about the last scenario, which, if you think about it, the last scenario would be what happens if there is some kind of external force. And if there is some kind of external force, then what we have is the following, is what we call forced oscillation. And this is the last case we're going to consider. And after that, I'll probably go end today's video a little longer, but then that will mean that I don't have to give you a third videos. And I'm just going to give you the third days to just go through your homework so that you can see some of these problems. The way the problem work out is exactly the same as what you did on 11.2, 11.3, where you're solving homogeneous and non-homogeneous differential equation. And as a matter of fact, in this case, all the solutions are already set up for you. All you have to do really just plug in numbers and use the formula. So it should be pretty straightforward. So the last case is what we call force oscillation. So when an external force is being applied, to the piston, we have a forced oscillation. And what happened is the following: the resulting differential equation is non-homogeneous. And lucky for us, when you have a non-homogeneous differential equation, then what happened is the solution will basically be a superposition between the homogeneous part and the particular solution, based on what we learned in 11.3. The solution can be described using the superposition. Remember what does that mean by superposition? Meaning adding the superposition of the homogeneous solution and the particular solution. Now, however, something interesting that I do want to point out is important to realize the following. It is important to note that for k greater than 0, the homogeneous part will almost guarantee to contain e to the negative k over 2mt. And if you think about it, it makes sense if you think about it. Right here in the critical damping case, we have that. In the underdamping case, we also have e to the negative k over 2mt. Okay. And then in the free oscillation case, we don't have negative k over 2m, but we do have, let's see. Okay, this is a free oscillation. So free oscillation doesn't have that because then you have two positive value. But in the damped oscillation, we would definitely have the negative or negative 2 root R1 and R2. So they would probably be some kind of negative k over 2m plus or minus some value, but they both have to be negative. Now, why is that important? Well, important to note that that is the case. The homogeneous part often contain e to negative k over 2mt. And the important part is this, which as t increases to infinity, e to negative k over 2mt would approach 0. And so what does that mean is that it implies that as t go to infinity, the homogeneous solution will approach 0 and therefore have no effect on the entire solution, because it just keeps getting smaller and smaller and therefore have no effect to the overall value of the solution. And when that happened, we would call the particular solution, which is more important because the homogeneous part eventually tend to zero, the complementary particular solution will basically dictate what's happening to the piston, and is therefore usually referred to as the steady state solution. And if you think about it from a physical standpoint, what does that mean? Meaning that when you have a force oscillation, eventually the external force would dictate how the oscillation would work. Because the homogeneous part, which is basically what the initial value started the oscillation, will eventually just die off based on the fact that the friction would eventually slow it down so that it would have no effect, and so the external force becomes the only force that pushing the piston back and forth. And that's why it's called a steady state solution. Unfortunately, that's all the time we got, so I'm going to go ahead and stop right here. And as I say, probably just going to give you the next day, instead of give you a video, I'm just going to give you class time to work on your homework so they can do some of these questions and try them out and ask questions during class. All right, I'll talk to you guys later. Okay, bye-bye.